Hello, and welcome to the EMC Live Roundtable, HEMP, IEMI, and the Critical Infrastructures Part 2. My name is Dawn Hoffman, and I'm the Marketing Manager of Interference Technology, the creator of EMC Live. I hope you were able to join us yesterday for the first day of the event, and we welcome you to join us this afternoon and tomorrow for many more informative and practical webinars. This roundtable is moderated by Dr. William Radasky. Dr. Radasky received his PhD in electrical engineering from the University of California at Santa Barbara in 1981. He has worked on high-power electromagnetics applications for more than 46 years, beginning his career as a research officer at the Air Force Weapons Laboratory at Kirtland Air Force Base, New Mexico, from 1968 to 1972. He has published over 450 reports, papers, and articles dealing with electromagnetic environments, effects, compatibility, and protection during his career. In recent years, he has worked extensively by performing assessments for several critical infrastructures to the threats of HEMP, IEMI, and severe geomagnetic storms. He recently led two working groups that produced a technical brochure on the protection of power substations from IEMI and also an IEEE standard for the protection of computer systems from IEMI. He founded Meditech Corporation in 1984, for which he is the president and managing engineer. Our panelists joining us today are Dr. George Baker and Mike Caruso. Dr. George Baker has been involved in electromagnetic protection research, management, and education since 1973. He is Professor Emeritus of Applied Science at James Madison University, where he has served as Technical Director of the university's Institute for Infrastructure and Information Assurance. He is a founding member of the Virginia Alliance for Secure Computing and Networking and the Directed Energy Professional Society, and an EMP Fellow of the Summa Foundation and senior member of the IEEE. Mr. Caruso is Director, Government and Specialty Business Development for ETS Lindgren. He is a recognized leader in the RF shielded enclosure anechoic chamber industry with 32 years experience in project management, technical applications, and business development. Mr. Caruso chairs ETS Lindgren's HEMP EMP product team and has been involved in ETS Lindgren's Red Edge product development. This roundtable will be interactive, and we do encourage you to ask questions. Take a look at your GoToWebinar navigation pane, the box on the right hand of your screen. If at any time you have a question, please type it in the text box and hit send. To minimize or maximize your screen, click the arrow button. We will discuss this topic for 45 minutes. Now, Bill will begin the presentation.
Okay, thank you very much. I'll start here with an overview of the roundtable before we get into the details of the talks. Just with a little background, a lot of us, of course, are EMC folks, and we know that we live with electromagnetic environments every day, including radio, mobile phones. And while these are beneficial to society, we have to be aware that transmitters of any kind can cause effects on electronics, but fortunately, in most cases, our electronics are at enough distance from these transmitters to operate without problems. There is, however, a caveat. Modern digital electronics cannot tolerate high levels of radiated or conducted electromagnetic threats without some protection. And unfortunately, or fortunately, we could say either way, digital electronics are now a big part of our critical infrastructures, especially in the control sides. And in particular, the electric power system, which has been referred to as the keystone by the EMP Commission, and we'll discuss that a bit later, but also communications, financial, transportation. There are many, many infrastructures that are very important. In the past, when we talk about high power electromagnetics, high power, not high energy, but high power, peak electric fields that are very severe, these were provided, if you will, only by lightning, electrostatic discharge, and radar. All of which can be very serious if the lightning is close. The ESD is on electronics, it's not well protected, and radar, of course, being close to radars can be difficult for normal consumer electronics. But today, and the purpose of this roundtable is to discuss the threats of high altitude EMP and intentional EMI for the critical infrastructures. I want to discuss a little bit of terminology in this introduction. Electromagnetic pulse actually is a very old term, but it was used starting about 40 years ago to describe only the electromagnetic signals from a nuclear detonation at any burst altitude. And the military, in its work, has defined HEMP for high altitude EMP, SREMP for source region EMP, system generated EMP, internal EMP, and many other terms. And the reason for these acronyms were there were very specific military systems that had concerns with different types of interactions of electromagnetic pulse. For our interest, the high altitude EMP for commercial applications, HEMP, is the most important. It's been used to describe the electromagnetic signals from nuclear detonations above 30 kilometers, basically in space. The biggest concern about HEMP is that these high altitude bursts, one or two, can cover an entire continent, and they will have effects on electronics on the ground, but not directly on people, i.e. the radiation is not reaching the ground. Unfortunately, in recent years, popular press articles have started to call all electromagnetic threats as EMPs, and this provides confusion. You've heard EMP bombs, which are usually non-nuclear but usually explosive. Electromagnetic weapons, which are non-explosive but can fire many times, and even geomagnetic storms have been included in the category of EMP. And if it's not clarified, this can be very confusing in terms of what we're speaking about. So in this presentation, and also in many formal standards and documents, the IEC, the IEEE, and SIGRE, we are using official definitions which include HEMP, high altitude electromagnetic pulse, that is from a nuclear detonation in space, and a second category, intentional electromagnetic interference, IEMI, which is caused by the use of nearby electromagnetic weapons by criminals and terrorists. And we'll get into a little bit more detail about those later. The outline of this roundtable is that I'm giving this overview right now, and then there'll be three main technical components. First will be the basic threat features for HEMP and IMI, but also some discussion of the similarities and differences, and I will be presenting this. The second presentation will be the early time E1 HEMP and IMI high frequency protection measures, similarities and differences by Mike Caruso, and common misconceptions concerning HEMP by George Baker. Okay, so I think that is all for this presentation, and I will move directly into the threat presentation. This is excuse me, basic threat features for HEMP and IMI, similarities and differences. Excuse me. First, here is a generic plot of the high altitude EMP environment terminology. As you can see, this waveform extends for a great deal of time, from 10 to the minus 10th to about 10 to the 3rd seconds. Excuse me, I have a bit of a cough. I apologize. As you can see, this is a logarithmic plot in time, but also in amplitude. And while at very early times we have a large peak value in tens of thousands of volts per meter, the waveform continues. And in fact, we have denoted in the HEMP terminology, and this is also is in the military, but also in the IEC, which writes standards in this area, the early time, the intermediate time, and late time. And the shorthand, we refer to these as E1, E2, and E3. I should also note that while we see very low signals here in the 1 second and beyond time frame, these signals are very important to the way they interact with the electric power grid and can create problems. There will be only a little discussion of that during this presentation. Most of the presentation will emphasize the early time E1 HEMP. In terms of historical evidence, in the 1960s, the United States and also the Soviet Union did testing at high altitudes with nuclear devices to see what effects may occur. The motivation was to see if there were any impacts on electronic systems, but actually were mainly focused to acquire data on communications and other aspects of a burst in space. The Starfish event is one of the ones in which the basic details have been released by the government. Rocket launch from Johnson Island in the North Pacific, 1.4 megatons at 400 kilometers, 1,400 kilometers from Honolulu. There were modest effects noted in Hawaii. The photograph is actually taken from Honolulu on a hill. The bright spot is the moon, but the colored lights in the sky are a typical aurora type display from the charged particles that were emitted from the burst. The effects that occurred, the coupling to the Hawaiian electric light grid, turned off some of the street lights in Honolulu. There were microwave telecom outages. There were other nuisance effects. A lot of people have said, well, this is not very dramatic. Why do we care? Well, it turns out that we also measured the fields, the electromagnetic fields from these bursts, and we built simulators to produce those fields over many years. And it turned out that systems with modern electronics were tested, often showing more severe impacts than those we saw back in the 1960s. And that's really the root of the problem. The other thing that's important about the high-altitude EMP, since the burst may be detonated at very high altitudes, in this case 170 kilometers, there is a very large coverage. We see a generic circle based on the line of sight and the curvature of the Earth. So basically, one per burst can produce fields over an extremely large area. This is very important. I should also mention the EMP Commission in the early 2000s, 2001 through 2008, studied the effects of high-altitude EMP on the critical infrastructures, and these are their conclusions, paraphrased from their conclusion aspect of their report. One or a few weapons can simultaneously, over a wide area, produce potential problems in electronic systems. And in particular, this was focused on the power system, where we could see failures of the power system, but also telecom and financial. And this would occur very quickly and rapidly. There would be cascading failures where effects would propagate to other aspects of the power grid, for instance. And they pointed out that it wasn't just the civilian infrastructure that was of a concern, but the military also depends greatly on the civilian infrastructure. And their point was that without adequate protection or planning, full recovery of our economy could be prolonged. So now I will switch to the intentional EMI. And here it's a relatively new term. Most of us in the EMC business know EMI, electromagnetic interference. This is when we have a failure of electromagnetic compatibility, EMC. This is a definition that took quite a bit of time and effort to come up with. It is officially in an IEC standard. It was first mentioned in February 1999 at the Zurich EMC Symposium. But the main features of this are intentional, malicious generation of energy, and it's to introduce not only damage, but noise signals that can disrupt, confuse, or damage. Damage, obviously, is the worst case, but it is also possible to disrupt and confuse, and this is important. What makes the IMI threat? Basically, electromagnetic weapons that have an energy source, batteries, capacitors, and an antenna. Obviously, how well those are put together determines how big of a threat you have. But these are designed to propagate electromagnetic fields to a significant distance. They've mainly been designed in the past for military purposes, but unfortunately, like a lot of things in technology, the basic physics is well understood, and it's not difficult for a qualified engineer to design a weapon. The other bigger problem, though, is that commercial electronics are not protected against these types of threats. So over the years, the last 15 years, intentional EMI has been a term used to describe this threat to commercial electronics. In terms of weapons, there are real weapons. There are companies that build them for the military and other applications. Here is an example of a suitcase device, which has been extended, as indicated here. The field value of 120 kV per meter at 1 meter is very strong. It decreases as 1 over distance, so at 10 meters it would be 12 kV per meter. But this is a very old device and has been extended a factor of 4. So we're talking about 50 kV per meter at 10 meters, 5 kV per meter at 100 meters. This is a very significant source. It has a repetitive pulse. It's fairly small. The next device, which has been published, and these are published cases, the Air Force Research Lab developed in, I believe, 2005, 10 years ago, the most powerful device of its type, which is carried on a small vehicle. And this one is 10 times bigger than the small suitcase device. So these are extremely powerful devices. We're only using them as examples to understand what might be done to aid in assessments of facilities. In terms of interactions, the interaction situation involves the possibility of someone in a parking lot in a vehicle with a van that can generate electromagnetic fields surreptitiously. They can couple to lines, power and communication lines outside the building, and then insert transient voltages into the power and communication system. These fields can also penetrate the building unless it's a shielded building, whether it's windows or walls. Wood and so forth does not provide much protection. There may be some protection from concrete, but it's minimal. And once these fields get inside the building, they couple to the cables and can inject large levels of voltage and current into equipment. The examples shown are actual tests that were done on electronic systems that show the types of effects that can occur, including physical damage, as seen in the upper right. And these are for levels that can easily be generated by electromagnetic weapons. Now, we've mentioned a bit about HEMP, a bit about the intentional EMI. One thing I did not mention is the intentional EMI waveforms. The threat weapons typically can produce 2 categories, either wideband, single pulses repetitively pulsed, or narrowband. You can see this on the right side of the frequency domain figure. The high altitude EMP, E1 early time is shown, and for reference, the electromagnetic fields from a nearby lightning. And of course, all of these can vary. These are generic plots. However, the most significant aspect is that both the high altitude EMP and the wideband and narrowband electromagnetic weapons are at much higher frequencies than lightning. And this is significant because most buildings, even homes, have some protection against lightning. Commercial facilities have much more, but the grounding and protection aspects of lightning are at a much lower frequency. And this means that the types of grounding and so forth are not sufficient for the higher frequencies. So this is a serious concern that we have to examine in the future. As you look at HEMP and the electromagnetic threats producing IMI, you can see that the IMI is even at a higher frequency than the high altitude EMP. And this is one of the differences that needs to be treated, although it's not a serious threat, as I'll explain in a few minutes. The similarities of HEMP and IMI, both of them produce very high level fields in excess of 10 kV per meter. The E1 HEMP fields and the IMI fields can typically couple to unshielded buildings with very little attenuation, and this has been measured at many facilities. They also get into cables and electronic equipment through small apertures. Commercial equipment is not naturally hard, protected, although some equipment can survive. And both of these threats can be defeated by high-quality electromagnetic shielding as developed by the EMC community. Normal shielding will work. It doesn't have to be special hemp shielding. Differences, obviously E1 hemp requires a nuclear weapon, whereas electromagnetic weapons can be built in a laboratory using modern switches that are readily available. E1 hemp typically is a single pulse, although a very long pulse, while most electromagnetic weapons can produce multiple pulses. A big difference is the frequency content. The hemp goes to about 1 gigahertz. The EM weapons can go up to 10 gigahertz. The E1 hemp also produces simultaneous fields on a continental scale. Electromagnetic weapons are local and mostly effective within 100 meters, but they can be fired multiple times and used many, many times at different locations. Electromagnetic weapons do not effectively couple to long power communication lines, whereas for E1 hemp, this is very important. So that's a significant difference. The other and last thing, which we have not spoken about since the beginning, hemp also produces a late time field that effectively couples to long lines and may create a damage threat to large transformers, along with possible large-scale blackouts. This is very similar to the geomagnetic storm. So, threat conclusions. While there's some differences with regard to these two EM threats, their similarities are stronger. They both contain higher frequency content than typical natural threats, lightning. Commercial electronics nor the buildings do not offer much protection against either of these threats, although lightning protection is often designed into new buildings. And it appears reasonable to protect against both threats through the addition of electromagnetic shielding and penetration controls, while being sure to include the range of frequencies for both threats up to 10 gigahertz. And we'll hear more about this later. Thank you, and I guess we should move on to the next talk with Mike Caruso. Hold on. And here. Mike, I'll hand it over to you.
Thank you very much, Bill, and thank you everyone for listening to this webinar today. What I'm going to, next slide please. What we're going to look at today is basically some of the various points of entry that are used in building an EMP shield, and I'm using the generic EMP to just incorporating HEMP and IEMI, but we're going to look at the differences between some of the points of entry treatments for both of those. Next, please. As Bill had pointed out, the frequency domain of the two are somewhat overlapping. In this, we're seeing the bottom pink color trail is actually the IEMI. So as Bill had pointed out, that can be up to 10 gigahertz, whereas the IEMI does not have the E3 component to it. It has an overlapping component of E1 and E2. The IEMI devices can be very devastating. Next, please. As Bill had pointed out, you know, we in the EMC world deal with immunity for equipment, and these are just some examples of the harmonized immunity standards that are in place around the world for equipment. So you can very easily see that if an HEMP or an IEMI would produce fields in excess of 10,000 volts per meter, the standard equipment is really not designed or built to accommodate that kind of pulse. Next, please. So what we're looking at is the modern electronics are very susceptible to the HEMP waveforms. So what we do look at in some cases is building shielded environments in which just the equipment inside the shielded environment is protected, while the support utilities for that equipment could remain vulnerable in the facility. So in an event, the utilities would go down, but the equipment in the shielded environment would be protected, and when the utilities were restored, the equipment could be put back into service. But then we also look at the ability to operate through an event. And that's very important to many folks, especially if they're running a Tier 4 data center. And in that case, what we do is protect the backup power, the backup cooling, and all of the communications that would be going on as well. Next, please. These are just two examples of the various types of shielded enclosures that get used. On the left, we have a welded enclosure in which metal plate is used and all the seams are welded. And on the right, we have a modular enclosure that is a bolt-together system that would provide the same sort of shielded protection needed. But I might add the bolt-together enclosure does not meet MIL standard 188-125 requirements because it specifically requires welded. Next, please. These are some of the waveguide air vents that are used, and what we want to look at is the performance on these. And as we had talked about, the IEMI can reach up to 10 gigahertz. So you see on this chart, at 1 gigahertz, we're looking at 120 dB of protection from 3/16 inch honeycomb, but we're getting that same 120 dB all the way up to 18 gigahertz. So the 10 gigahertz gets covered very nicely. So this is a waveguide vent that would be used in both cases, and very similar threats. Next, please. We're looking at waveguide feed-through penetrations for the various systems, and this is where we have to be careful because if we look at the chart, we see at 4 inches, and I have to remind everyone that we at ETS anyway use a 6-to-1 ratio, so the length of the penetration would be 6 times its greatest opening. And in this case, if we look at a 4-inch penetration, it would be 24 inches long, and cutoff would be 1.7 gigahertz. So it would cover the 1 gigahertz for the HEMP, but it would not cover the 10 gigahertz for IEMI. And a lot of times in design, we use a 6 gigahertz number for IEMI. To look at penetrations. Next, please. So I did go through those slides very quickly, only because I do have another webinar following this at 1:30 p.m. Eastern Daylight Time, and I'm going to be talking more about the mitigation methodologies and products that are available and how they're used for HEMP and IEMI. Thank you very much for your attention.
Okay, thank you, Mike. And let us move on to our last presentation. And let me introduce Dr. George Baker. George, if you could take over.
All right, thanks, Bill and Mike. And I want to talk about a number of misconceptions about EMP that are routinely advanced by both the technical and policy communities. And you see these in press reports, you see these on preparedness websites, and even embedded in technical journals. And because of many aspects of EMP, and I'm going to be talking exclusively about nuclear EMP, what Bill calls HEMP, because the physics and its effects are obscure and non-intuitive, misconceptions are inevitable. But the ubiquitous effects and number of systems potentially affected make it convenient to adopt misconceptions that avoid the need for action. And so my hope in what I'm going to present today is that correcting the most important and pervasive misconceptions will help to spur action to protect our nation, and public-private cooperation will prevail in implementing protection of our most critical infrastructures. So my first misconception, EMP will fry every exposed electronic system. We have test databases that have been compiled over the years within DoD, and also the Congressional EMP Commission developed a test database, and we know that smaller self-contained and self-powered systems that are not connected into long-line networks, these would include vehicles, handheld radios, disconnected portable generators, will often survive EMP without any special protection. And if there is an effect, it is more often temporary and rather than a permanent component burnout type effect. The threat level testing, though, also reveals that if you have a system that's connected into a long line network, this system is highly vulnerable in most cases to upset or component damage. The longer the line, the higher the probability of damage. And of course, power grid and long line landline communication systems will be the most vulnerable to component damage, with cascading effects to most other infrastructure systems dependent on power and communication. All right. Next, misconception number 2, that EMP effects will be very limited. This is just the converse of the first misconception. Effects will be very limited and cause mostly easily recoverable nuisance type effects. And there's a corollary misconception that I hear that EMP will cause only upset effects, temporary glitches rather than any kind of permanent effect. It's true that although EMP doesn't affect every system, you can still get widespread failure because of the interconnection between system electronics boxes that fail and those that don't. And so there's a theory, a network theory called small world network theory, developed by a brilliant mathematician, a very prolific mathematician, Paul Erdos. And there's a graph in this chart, the lower graph, that illustrates the average fraction of nodes in any network that are connected to any single network node will change suddenly when the average number of links per node exceeds 1. A node is just a point in the network and where something is connected. And when the average number of connections per node goes up to 2, you'll notice that a failure of that node can affect 50% of the remaining network nodes. So you don't have to have every node fail, but if you just have a few nodes fail, you can bring down the entire network. And that's the gist of Erdos' theorem. Also, for many systems, especially unmanned systems, upset is tantamount to a permanent damage. And this is also true for industrial control systems. So, for instance, if you upset the pipeline pressure controls, you can actually get fires and explosions from an EMP. Or if you cause generator controls to malfunction, you can actually cause the generators to self-destruct, as was illustrated in the Aurora test done at the Idaho National Labs. Next, misconception number 3. I've heard several people say that it takes megaton class strategic weapons to cause any serious EMP effects, and that's simply not true. There is a limiting atmospheric saturation effect in the generation process such that low-yield weapons produce peak E1 fields, the prompt pulse, of the same order of magnitude as large-yield weapons. And for instance, if you look on the left, if you raise the yield from 3 kilotons up to 3 megatons, that's a factor of 1,000 increase in yield, you only get a factor of 3 increase in the peak E1 field. And these small entry-level weapons can give you quite appreciable EMP fields. The second graph there on the right indicates that megavolt levels and kiloampere currents can be induced in long overhead lines by kiloton class weapons. Next misconception, number 4, that to protect our critical national infrastructure would cost a large fraction of the U.S. GNP. This is not true. If you look at the 14 critical infrastructure sectors, the risk is highest for electric power, and telecommunications. And so attention to these alone would bring major benefits to national resiliency. They're the most vulnerable due to their organic long lines, and they're also the most necessary if you talk to the emergency response crews for recovery of other infrastructures, lifeline infrastructures. So very important. So if we had to pick one, I would pick the electric power grid. If we could protect that, at least get the lights on so we could see to fix the others. And the reason is the electric failure of the electric power grid is very brittle, where the communication systems are more malleable. And the power grid fails very quickly and hard over large regions. And so it turns out that if you protected the components that are most difficult to replace, that would buy very much valuable time, and that would include the high voltage transformers and generators in the generation plants. And so that there are estimates that you could protect the heavy duty components in the grid for single-digit billions of dollars, which, if you amortize that over the entire customer base, would amount to pennies per month for electricity consumers to affect that protection. Let's go to the next misconception, that operational procedures are sufficient to protect the electric power grid. The electric utilities, the dominant view of the electric power industry is that they can handle any EMP and GMD effects just by having some field expedient operational procedures, and that's a problem because there's a legal problem. One of the operational procedures is to shed load, that is to turn off power to blocks of customers, and grid operators will be very reluctant to do this because if they do, then they will be liable. If they just wait and let the EMP shut the grid down, they would not be liable. So there's a built-in liability problem with relying on operational procedures. The warning time is insufficient. The entire Northeast went down with a single point failure of a tree branch problem, and with EMP or GMD effects, you would have thousands of failure points simultaneously, so that that amount of warning time would not give you enough leeway to affect the operation procedures needed. And the problem is that there's a draft. Actually, it's been approved now. There's a NIT operational procedure that it doesn't apply to the generator authorities or load balancing authorities. So even the operational procedures are not going to be in place for large portions of the grid. So there's a problem there. Next. A misconception that optical fiber networks are not susceptible to EMP effects. Again, this is not true. In general, they are less susceptible than the metallic line networks, but the fiber optic line drivers and receivers at the ends of the lines are susceptible. And the long-haul telecom and internet optical fiber repeaters over continental links, those repeaters are susceptible. On the plus side, the line drivers and repeaters are relatively easy to protect, and with your standard shielding, aperture treatment, and power line filters. So here are some misconceptions that we need to get beyond these and to get our plans in place to address the EMP.
Okay, George, thank you very much. This completes our presentations, and I guess it is time to see if there are any questions or comments from the listeners.
Thank you so much, gentlemen. You must have covered the topic pretty thoroughly, though, because we have not received as of yet any questions. So would you like to take the last 5 minutes or so to elaborate on anything or discuss the topic further?
Let's see, George, do you have anything further to say about the misconceptions?
I think I pretty much covered the waterfront there. There's a tendency, the main tendency now, to downplay the threat, and that puts EMP preparedness on the back burner compared to other effects. And so that's a problem. That's a problem that we need to get beyond that.
Yeah, I think that's right. One other comment I should make, in your last chart, you were talking about geomagnetic disturbance. As I mentioned before, we have geomagnetic storms, which is a very low frequency event, but also the E3, the late time part of the hemp, produces a very similar signal. So
Right.
there's a parallelism there that is very significant and needs to be considered in the future. And it turns out that NERC has moved fairly quickly on the GMD aspect, and while maybe it is not complete and so forth, there's no indication of similar activity for the EMP part. I don't know if you want to comment further on that, George.
Yes, we're in a mode where we have, I call it run around the rosy. You go to NERC and say, well, we need to include EMP in the protection of the grid, and they will say, no, well, that's DOD's responsibility. And the DOD folks, a lot of them will say, no, really, that's Homeland problem. That should be DHS. And then you go to DHS and they say, well, our SSA, our Infrastructure Sector Authority, is DOE, and DOE should be required to do this. And then it goes come full circle. We need to have some organization with EMP in its name to be the focal point for this. And that until that happens, I think we're really sort of in a world hurt here.
Yeah, I think so. I mean, one of the things that the EMP Commission did was it made many recommendations for things for both commercial and military to move forward, but there's been not a great deal of action with regard to that, which is unfortunate. I know there's been some. Yeah, I know there's some suggestion that maybe the recommendations of the Commission should be re-examined to see about progress, but I don't know if much is happening there. The other thing yeah, go ahead, George.
Yeah, the other point I want to make is a lot of people, when they hear these presentations, they think that we're SOL, there's no hope, and that is nothing could be further from the truth. The engineering, we know how to protect. We can do some very important things for a reasonable amount of money, and so this is an avoidable. These kind of catastrophes are avoidable if we just bite the bullet and protect our most critical systems.
Yeah, that's exactly right. One other comment, since we were emphasizing high altitude EMP and intentional EMI, there's a lot of interest coming now that since intentional EMI comes from electromagnetic weapons nearby, it's just another component of a physical attack. And we're seeing a lot more interest from commercial facilities to consider this as just an extension of normal security aspects, that you lock your door, but now someone can, from outside the door, attack your equipment inside, whether it is for financial gain or just to give your business a problem. And so I think it is important, as we've described in this presentation, to see the similarities for the early time hemp and the IMI, where if you can really look at protecting against both of those at the same time. And I think that's an important aspect that people should recognize. Mike, do you want to comment on that yourself?
Yes, thanks, Bill, and certainly agree. We've seen tremendous interest, particularly from financial institutions and utilities, the part of the critical infrastructure. But one of the points that I didn't make is that in all cases, you're going to need to make sure for points of entry for copper connections, particularly electrical power, you're going to need filters that are fitted with MOV devices.
Okay. Well, thank you very much. I think we've come to the end of our time. Jacqueline, is there something further we need to do here?
No, actually, we did receive a few questions last minute, so I will send those over to you guys and you can address them and we will get those out to the viewers. So attendees, please join us at 1:30 Eastern Daylight Time for the next webinar that Mike will be presenting, Early Time HEMP versus IEMI Protection Measures. How are they similar and different? Also, attendees, if you do have any more questions, please send us an email at info@interferencetechnology.com. A recording of this webinar will be available on our website, emclive2015.com, and we will also send a link to all the participants. Thank you for attending.